Okay, so I want to do a quick review over electric fields because we haven't read about them or talked about them in a mathematical sense since last week when you were supposed to read 16.7 and 16.8. So I'm going to do a really quick recap of those. So the electric field is represented by a capital E. And that's just an area or a region around a source charge where an electric force can be measured. Another way of putting this is that it's a vector field that graphically shows the magnitude and direction of the electric force on charges in an area around that source charge. And you can pause here for a moment if you want to write some of these down, but you should already have this in your notes. It's also called an E field, and it's created by a source charge. We've used the symbol lowercase q. We also have seen a capital Q for this. Not my preference in our class because capital Q represents heat, so we are trying to stick with lowercase q's as we're doing our work. The EO field is measured in units of newtons per coulomb, and so you can see this is a force per unit charge here. And we're going to find that there's a direct relationship between the field strength and the charge, and that there's the relationship between the distance between the charges and that field strength follows the inverse square law similar to that we saw in Coulomb's law and the law of universal gravitation. All right, mapping an electric field, I want to go back through this again just to refresh a couple of points that seem a little inconsistent for some students. We take a source charge, we look in this area around the source charge is where we're going to have that electric field. We can diagram that field just like we did with magnetic fields. But we need some kind of test particle, and by convention we use a positive test charge, very small so that it's not having any influence on anything. And we put that positive test charge in the area around our source charge, and we look at how it's affected. And the E field, the direction of the E field, is the direction that that test charge is going to be pushed or pulled by that source charge, or we could say the direction that that positive test charge will accelerate when it's placed in that area. And so we know if we have a positive test particle and a positive source charge, they're going to repel each other, so the field at that area would be away, and in this case up. And these are three-dimensional, just like our magnetic fields were three-dimensional. And we can actually do this all the way around the sorry, I didn't mean to flip that quick, all the way around the source charge to look at the direction in three-dimensionally. I'm not only going to do two dimensions clearly on the screen, and what we would see is that we would have an electric field which is radially outward, points radially outward around our positive source charge. Okay, our electric field lines, if we've got multiple charges, we're always going to start on a positive charge and end at a negative charge. If there's only one, we don't have this sort of starting and stopping. The electric field lines never cross, and they can't cross because we're using a physical means to determine them. So if the field lines crossed, it would literally say that that particle would accelerate in two directions at the same time, or would experience a force going in two separate directions at the same time, and that's not possible. So it's really important that they don't cross. When dealing with two electric charges, we've already seen that our field lines kind of bend or curve to ensure that they're not crossing over one another. And those are much better in illustrations than we can typically hand draw, but please try to do your best. The number of field lines starting from a particular charge or leaving a charge is proportional to the amount of charge. The more charge there is, the larger the source charge, the more field lines there's going to be. The smaller the source charge, the fewer the field lines. And that should make sense, that the more charge you have there, the stronger force that it's going to be able to create. Okay, so around a negative source charge, our field is going to point radially inward because that positive test charge is going to be attracted. And again, this is just a review from last week. Recall also that our spacing of our field lines indicates the field strength. The more closely packed together they are, the stronger the field. The stronger the field, the larger the force it exerts in that area. The farther the lines are spread apart, the weaker the field. The weaker the field, the weaker the force. The smaller the force it exerts in that area. All right, flashback last week to Coulomb's law. And we said that, excuse me, a force on a test particle, we're going to call that Q naught for now, that force on the Q naught was equal to Coulomb's constant times the first charge, in this case it's the source charge, times the test particle, Q naught, divided by the distance between them squared. Now we've learned that we can calculate the magnitude of the electric field of that source charge by looking at the force it exerts on a test particle divided by the size of that test particle. And remember, our units were newtons per coulomb. And so now you should notice here that I have a connection here through this force, and so we're going to derive a formula, and you should do this in your notes because you will need to derive this on the test. You will be given Coulomb's law. You will be given E equals F over Q. You need to be able to derive the next formula. So let's do it together. We're going to take this KQ Q naught over R squared right here, and we're going to insert it here for the force on that test particle, just like this. And so when we do that, we should see that R squared is going to drop to the bottom. And then you should notice there's something going to happen to Q naught. So of course Q naught is in the denominator and the numerator, so they're going to cancel out. And that leaves us with this third formula here, that the field, the electric field of that source charge, is only related to Coulomb's constant times the magnitude of the source charge and divided by the distance you are from that source charge. And this is really, really important and should be sort of similar to your experience when we calculated local acceleration due to the gravitational field, little g, back in first semester when we calculated little g. We saw that little g was dependent on the mass of the planet, or the mass that was creating the gravitational field. That acceleration due to the gravitational force was not dependent on the masses you were sticking on the Earth or near the Earth or near this other mass, but just on the mass that was creating the field. Our field is only dependent on the source charge. And so this formula is what allows us to go back and calculate the field strength or the force at a given point in the field without really knowing how much stuff we're going to stick there. And so you saw that last week when you were answering those conceptual questions from Giancoli, that you had to calculate these things where you had to kind of look at the field diagrams and you looked at the density of the field lines and were trying to determine whether things were stronger or weaker. Now we actually can calculate. We don't have to know how much test particle we're going to put there. We just have to know the size of the source charge and how far we are going to be away from it, and we can calculate anything we want. Okay, some reminders when you're doing these formulas. Do not use the sign for the charge in the formula. You'll draw the scenario and determine the direction of your vectors by looking at your diagrams. Now, I'm going to try to do a couple of problems on a separate video, but I've been having a little bit of issues with my cursor here, so whether or not I get that uploaded we will see, but if I don't, you have a perfect example on page 451. 16.7 is a great example that shows you that you need to look at your diagrams to determine the direction, not plug your signs in. Last week's video gave you a convention that was very complicated to remember it. If you want to do it that way, that's fine. That's not how I recommend it, but that's your choice. If you're finding a net field between, there's multiple charges, multiple source charges, and you're trying to find the net electric field at some place around those different charges, then you need to remember these things are vectors. Electric fields are vectors, electric forces are vectors, charge is not a vector, it's a scalar quantity. But the vectors, you need to take the direction into account when you're finding net field, just like you did when you're finding net force. But again, we're going to do this manually. Again, there's an example on 16-8 on page 452. Now, I'm going to stop this video and start a new one for the examples. I'm going to give you these two examples in a separate video, and then you will do your practice. Your practice is going to be collected at the beginning of class on Friday. I will be checking the work over the weekend, so this is considered classwork, not homework. I'm just giving you extra time to get it done. If you have any trouble, you can email me directly. You'll find your formulas that you're going to use on page 464. There are formulas 16.1, 16.3, 16.4a. Those were the three formulas we just derived, or that we just looked at. Coulomb's law, the electric field, and then the two formulas for electric field. Page 466, that's where your problems are. And these are the problems that are going to be collected at the beginning of class, and then I'm going to have them picked up for me so that I can look at them over the weekend and make sure we're on the right track. Page 466, problems 23 through 28, problems 31 and 32. So again, problems 23 through 28, and problems 31 and 32. And then the sub is going to play a separate video if I can get that done for you. All right? Good job, guys.